There is an invisible heartbeat running through the walls of your home right now. It is a perfectly synchronized 50 hertz cycle of alternating current that keeps modern society functioning. For decades, managing this rhythm was relatively straightforward. During the legacy era of the power grid, traditional machinery like incandescent bulbs and massive industrial motors drew power in a smooth, predictable manner. That predictability is disappearing. The rapid transition to green energy means our grid is flooded with new technology: solar panel inverters, battery storage systems, and millions of electric vehicle chargers. These devices are nonlinear loads. Instead of drawing a smooth, continuous stream of electricity, their internal components rapidly switch on and off. They sip power in jagged microbursts, thousands of times per second. This diagram on the right shows the result. A smooth sinusoidal voltage is forced through a nonlinear resistor, and the current, shown at the top, comes out warped and distorted. While these technologies are essential for the green energy transition, they leave behind a chaotic electrical footprint that actively threatens the stability of our entire infrastructure. Engineers call this electrical pollution harmonics. These are unwanted signals that vibrate at exact multiples of the original 50 Hz heartbeat, like 100 Hz, 150 Hz, or 250 Hz. The top two graphs break down exactly how distortion happens. You can see the clean, baseline 50 Hz signal being joined by individual, faster harmonic multiples. In a real-world system, these frequencies share the same physical wire, interacting in real time. The bottom graph shows the end result. When you mathematically add those overlapping high-frequency waves together, the smooth curve is destroyed, leaving a jagged, ruined waveform. Because the electrical grid is interconnected, these deformed waves don't stay contained inside a solar farm or an EV charger. They travel backward into the local grid, polluting the power supply for everyone nearby. Keeping the lights on now requires engineers to constantly filter out this mathematical noise before it renders the local power supply unusable. To understand why this matters, we have to look at the physical copper and aluminum cables carrying this polluted power. A clean 50 Hz current flows evenly through the entire cross-section of a wire, distributing the load perfectly. But high-frequency harmonic currents behave differently. Due to the skin effect, these fast-moving frequencies electromagnetically push each other away from the center of the wire, forcing the current to crowd along the extreme outer edges. This effectively chokes the flow of electricity. It forces the same amount of power through a fraction of the space, which massively increases the resistance of the cable. That resistance creates intense heat. Transformers begin to overheat, capacitor banks are instantly destroyed, and circuit breakers experience massive peaks, tripping for no apparent reason. Harmonic chaos is a physical force. It is actively degrading and melting the billion-dollar hardware that makes up the national grid. Melting hardware is expensive, but harmonics carry a secondary, hidden threat to the grid's data. The modern grid relies on a digital nervous system. Operators transmit high-frequency data signals across power lines to communicate with smart meters, substations, and automated control nodes. Those dedicated communication channels require absolute clarity. When harmonic noise from scattered inverters and variable speed drives spills into the grid, it often bleeds into those exact same dedicated frequencies. These chaotic harmonic signals physically overlap with the network's telemetry. They crash into the data signals, scrambling them until the information becomes unreadable. If these communications are jammed, control rooms lose visibility. Without real-time data, operators cannot safely steer power around the network during peak demand, increasing the risk of blackouts. Harmonics act as a dual-pronged weapon, degrading the physical muscle of the grid while simultaneously blinding its digital nervous system. To protect the system, engineers deploy countermeasures. Their first tactic is sheer grid strength, technically known as the fault level. Think of a weak electrical network like a narrow pipe. If you inject a small amount of dirty harmonic noise into it, the entire pipe is instantly polluted and overwhelmed. But a massive, highly connected network operates like a rushing river. It can absorb and instantly dilute that same amount of pollution without failing. This chart tracks grid responses to frequencies. The peaks on this curve represent natural resonance points, where harmonic noise is dangerously amplified. As the arrow shows, increasing the fault level shifts the resonance peak to a higher, safer frequency band, preventing amplification. Anchoring noisy industrial loads to the thickest, strongest parts of the grid is the first critical tactic used to contain the chaos. Engineers also use geometric traps to catch triplen harmonics, the 3rd, 9th, and 15th multiples of the base frequency. They use the delta connection, wiring transformers so internal circuits form a closed triangular loop. This geometric shape acts as a trap. The chaotic triplen frequencies enter the triangle but cannot exit. Circulating infinitely inside, they cancel out and safely dissipate as heat. Operators add a final layer of defense through strict mathematical regulations. Standards like the UK's G5/5 legally block the connection of any facility that tries to export too much distortion. Through physical traps, electromagnetic muscle, and uncompromising legal standards, engineers successfully isolate the chaos of modern technology, ensuring the grid's 50 Hz heartbeat remains pristine.